Welcome to section 1.4, equations of lines and modeling. So here we go. Let's say a line has a slope of negative 7/9, and we can say that's the m value, and y-intercept of x1, y1, 0, 16. Find an equation of the line. Well, you can just say that because we know the point slope equation form, y minus y1 equals m times x minus x1, then you can just plug those information into the formula. Here's the m right here, negative 7/9. Here's the x1, 0, and here's the y1, 16. Type that into Desmos, which you'll have to do later, and you'll get an equation that you can use and graph. Example 2, a line has a slope of negative 2/3. Say that's your m value, and it contains the point negative 3, 6. Here it is, negative 2/3, negative 3, 6. Find an equation of the line. This would be great. You can use it. Next one, find an equation of the line containing the points 2, 3, and 1, negative 4. Well, the first thing you would need, I think, is to find the slope. So use the formula. Remember to label your points x1, y1, x2, y2, because there's y2 minus y1 over x2 minus x1. Crank all that out, and you get a slope of 7. That's the slope. Another alternative that sometimes this is more helpful, especially if you're required to produce slope-intercept form, you can say y equals mx plus b, and you know what the m value is. That's 7 right here, but you don't know what the b value is. So you can plug in m equals 7 and take either one of these 2 points. I'm going to choose the first one because it's more convenient, I guess. 2, you can plug 2 right here, and 3 goes right here. And then because of that, you can solve this equation and figure out what b is. B is negative 11. I'd like you to write this out in y equals mx plus b form. Take the slope and the b value and write it right here. And that'll be the equation you can have. Next, parallel lines. So parallel lines, these railroad tracks, they never intersect. On a graph, what that means is that the slopes are going to be equal to each other. You can see here the slope is 2, the slope is 2. They're the same slope, and if they have the same slope, then they're going to be parallel. And even here, you're going to have slopes that are undefined. They're so steep that has no value of the slope. But if that's the same in both cases, then they're going to be parallel. Here they're not parallel. You can see the slopes are not the same, and they intersect right here. So that's not parallel. Slightly more difficult is the perpendicular lines. That's okay. This is what perpendicular looks like. You've got completely vertical and completely horizontal. They intersect here at a 90-degree angle. That's perpendicular. Even if it's kind of off a little bit, you can see here the slope of negative 1/2 and slope of 2 gives you 90 degrees. So what's the relationship between negative 1/2 and 2 that creates this 90-degree angle? Whatever it is, you don't have it here. This is not perpendicular. These are not 90 degrees because the slope 3/4 and negative 3 don't satisfy that condition that I'm going to talk about in a second. Here's the condition. If you want perpendicular lines, you need to have slopes that are two things. They have to be opposites and reciprocals. That means you have to have a positive and a negative, and then you also they have to be able to flip them as fractions. So 3/4 and negative 4/3, yes, these will create perpendicular lines. If you had a slope of negative 7/5 and a slope of positive 5/7, these would create perpendicular lines. A slope of negative 4 and positive 1/4, again, one is negative and one is positive, and then if you take the reciprocals of each other, then that would be, these would create perpendicular lines. Here are some examples that are not. And why are these not going to create perpendicular lines? Because the slopes, although they might be reciprocals, that's great, 1/2 and 2, you are lacking a negative slope. They need to be both, one has to be positive and one has to be negative. Here, one is positive, one is negative, but they're not reciprocals, so therefore they're not going to be perpendicular slopes. Here, I wanted to show you some mathematical models. This is actually probably the most important thing you might learn in math in class, how to take data and model it. So I'm gonna type into Desmos these values, and you should too. We're going to consider 1980 to be kind of the starting year, so that'll be year 0. And then 30 years later, the year 2010 will be 30. So I'm going to actually type in 0, 5, 10, 15, 20, 25, 30. And then we're going to type in 2.8, 4.2. That would be trillions of dollars, the GDP. And if you want to take a look what the model looks like, we'll plot these points, and we'll ask ourselves, can we basically like draw a straight line through these? If we had to draw a line, what would the best line be? This is a scatter plot, and when you try and draw a line through it, it gives you what we call a linear regression. And linear regression is a special kind of curve. And I know it's kind of weird to think of a straight line as a special kind of curve, but it is. A line, mathematically speaking, a line is a curve that's really straight. So anyway, linear regression is a special kind of curve fitting that involves lines. And what's curve fitting? Just finding a function that fits the data. We're basically trying to draw a line through this, or if we assume that it's linear, we can type it in and find out the best line that fits. Some lines are better than others. Some data lend themselves better to lines than others. So here is a completely perfectly straight line, and the way that we know that it's perfectly fits on one line is that we get an R value of 1. 1 means perfect. These R values are really what they're called correlation coefficients. So the correlation coefficient is 1, that's perfect. If it's 0.91, that's still pretty good. You can see that the dots are pretty close to a line. Here they're a bit more scattered. We get a lower R value. Here they're negative. So the way the math drops out, if you get a -1, then that'll still be a perfect line. It just have a negative slope. Negative 0.91, still getting further away from -1, but not too bad. And this is way chaotic, although the slope is negative. You'll see that on Desmos in just a second. But check this out. Sometimes curve fitting isn't really good for straight lines. Sometimes you get data that looks more like a parabola or an exponential equation or some other curve. And we'll talk about those in future chapters. But right now you can just say that the graph is nonlinear, because what you really want is some sort of curve, not some sort of straight line. All right. So stay tuned for Desmos and do exactly what I do on Desmos. Make sure you can bring Desmos back to class with a saved file and everything. I want to see them in class, and make sure you answer the Edpuzzle questions at the end so you can do the first problem from the assignment. By the way, I just wanted to throw it out there that before moving to Philadelphia, I lived in LA for 9 years. That's Los Angeles. It was a great time. All right, let's start off with parallel and perpendicular slopes. So let's start off with a slope and call it m and say that m is equal to 3. Click out of it and you get a slider. You can change it however you want. So let's first start off with one equation. We'll call this y1, and then let that be the slope of mx plus b1. And yeah, you can add a slider b if you want. So you can see changing the b value will make it go up or down, still with the same slope, and changing this will make it change the same slope. Let's make y2 have the same slope mx plus b2. Yes, I love sliders. Add the slider. So you can see here you'll never get intersections as long as the b values are different. You change the slope, and there are always going to be railroad tracks on some level. They're always going to be never intersecting. The only way they could possibly intersect is if the b values are the same and they line up on top of each other. Then you just have the same equation twice. But outside of that, you'll never get an intersection. That's because the slopes are equal and you've got parallel lines. But let's change this so that we have, let's calculate a second slope. We'll call this now m1. And we have to update this. Yes, we want to say m1. And we want this one to be m2. So what's m2 going to be? Well, we'll see. We can change it to different things. Actually, I'd like to calculate m2 to be 1 divided by m1. That would make them reciprocals. Oh, and let's make them negative by adding a negative here. All of a sudden, if you let m2 be a calculation of m1, then they will be perpendicular to each other. Always perpendicular, because they're always opposite reciprocals. You can change the b value, you can change the other b value, but it's always going to be the same. It's going to be perpendicular. let's change this to point slope form. So okay, so here I'm going to show you how to do a linear regression. Notice that I'm signed in right here. Notice that I've already saved it, and notice that I'm in projector mode. Those are a couple things to make sure you've got going first. And then what I'm going to do, you don't have to add this picture here, but it's fun to add pictures to your graph, but you don't have to do this. I'm just having it there for easy reference so that I can see it. I'm going to insert a table. This plus button helps you add all the different kinds of things you can add to a Desmos sidebar. Most of what you do when you type in is expressions, but if you just want to add a note, just some text as a line, you can do that. And if you want to add a folder of things, you can put that. This is how I added the image that you see here. But right now I'm going to go for a table. And so you can see there's x1 and y1. And so I'm just going to go down the x's are going to be the years. I'm not going to do 1980. I'm going to do instead 0, 5, 10, 15, 20, 25, and 30. And then you can see, so that's the years since 1980, as you can see right here. And then I'm going to type in the GDP in trillions of dollars. Great. And I don't need the picture anymore. You can see some of the dots right here. I'm going to zoom out a little bit. There they are. Great. Now, I'm going to type in the linear regression. I want to see how the y's relate to the x's, assuming that it's a straight line. So I'm going to type in y1. And the reason I do that is because I see y1 at the top of this list. And then I'm not going to type in the equation symbol. I'm going to type in this symbol right here. It's in the top left-hand corner of your keyboard. It's right next to the 1 above the tab. This is the approximately symbol. When you type it into Desmos, it knows that you were looking for a linear regression. Slope, y equals mx plus b. In this case, it'll be y1 is approximately equal to mx1. You can see it right there, plus b. Super interesting that all this pops up right afterwards. The line you can see goes pretty much right through these dots, and it gives you the slope m right here, 0.405, the best possible slope you could have, and the b value, 2.1, right here. So that's really great because it helps you figure out the linear regression. Now the r squared values are right here. You can see with an r value is very close to 1, that means if you had it at exactly equal to 1, that would be a perfect, all the dots would be completely perfectly on the line. But 0.99 is actually really close, and that's good. It means that you can see that this is a fairly linear model. I just also want to point out that that you can, if you want, put in different equations too. This symbol right here can accommodate more than just a linear regression like y equals mx plus b. You could put in a squared, like that's a parabola. You could even put in a plus, let's see, we call this ax plus ax squared plus bx plus c. You can see here that it assumes that there's going to be a parabola, and it gives you the r value and the a, b's, and c values. So this symbol right here, as we learn about different, or as we use different curves and different functions, just know that this symbol is going to keep on coming up over and over again. When we learn about parabolas, we'll do it like this, and when we learn about log functions, we'll just have this symbol with a log function over here, absolute value function, sine function, whatever function is that we come up with. You can even do the cubic version, to the third squared plus cx plus d x1. And you can see if you wanted to come up with a cubic function, it would look like this. So it doesn't matter the function. This symbol, what we might call the tilde or the approximately symbol, is going to come up over and over again, and it's good to use.